Thank you very much. I'm Peter Janssen, and I'm an associate professor of electrical and computer engineering up at Bucknell University. Prior to that, I was at Rowan University for 11 years. And then prior to that, I was in the electric power industry for about 20 years. Can you turn it up a little bit? Okay, great. That's a lot better. And so what I'd like to do today is, oh, wrong way, huh? Okay, talk a little bit about some of the features of the cell that we actually tested, the independent validators. Introduce you to the measurement analytical method that we use to determine the power outputs, and also to review some of the findings that we had as individual validators. And before I do that, I just thought that it'd probably be important that you knew a little bit about me, so maybe it'd be a little bit more credible to you. And I put a couple little blurbs in there about my background. But most importantly, my mission in life is to try to make affordable, sustainable living on the planet. Because and everything that I've done in all of my professional career and all of my jobs has been to try to do that. My main focus areas now are in smart grid, new technology research, sustainable transportation, and photovoltaic system optimization. But during my career, I had an opportunity. You can see here where you see MSE Rowan University in 1997. It was about 20 years ago at this time that I had an opportunity to develop a relationship with Bill Good and Randy Mills when I first went to their Malvern laboratory to basically try to debunk their technology, because that's my main job at the one of my side jobs at the utility was to go out and look at everybody who'd come up with the next perpetual motion machine, and then try to find out what they were doing wrong and show them what their measurement errors were and how they weren't using real science. And of course, once I met Randy and Bill and saw what outstanding science they were doing, it became very impossible to debunk. I ended up doing my master's thesis on their technology to show that it was a scalable phenomena in the Calvé calorimeters, if you might remember that, and also to basically to verify that the technology was real. It led to actually an investment by Atlantic Energy in the technology, and also to do some pretty great things. But before I just got into the technical detail, I wanted to bring this quote up, not because it's political season. And of course, John F. Kennedy made this very famous when he spoke to the Irish Parliament, and then his brother, after his death, made it very, very famous when he was running for president. It was changed a little bit, but it originally came from a George Bernard Shaw play. And one of the things that everybody pretty much knows, if they know anything at all about Dr. Mills, is that he's quite the Renaissance man. And he's one of the only people in my life who sees things and says why and figures it out, as well as sees things that have yet to be and say why not. And we're here today basically as a testament to his decades of commitment to creating a pretty much of a revolution in energy, which I'm proud in a small way to be a small part of. So let's talk a little bit about the technology as it existed, and this is a prototypical view, as it existed when it was tested by the validators. Three of us, I believe, are present in the room at this current time, and we'll talk a little bit about that. So if we take a look at the schematic, we see that it has all the same kinds of devices that Dr. Mills mentioned earlier were necessary . I got it right there. Thank you so much. I had it upside down. Great. So if you can see the electromagnetic pump, you can see the inductively coupled heater, which, by the way, inductive melting of metals, which you gave credit to the metallurgy industry for, was actually Hank Rowan. Hank Rowan was a graduate of MIT and founded Inductotherm, he and his wife, making induction melting furnaces in their garage before they actually turned it into a multi-million-dollar project company. And Rowan University has actually changed its name after a $100 million gift, the largest gift ever made to a public university at the time. And again, it was all induction melting. So here we are, seeing one of the actual great applications of it here in the inductively coupled heater. And then again, the silver oxide stream, which you saw, the two streams in the current pre-prototype, getting ready for market device. There was a single injection right here with the silver oxide stream. And if you look closely in the top of this vessel. You can see right up in here, that's where that little nozzle was to bring that out. If you look at the side view of this exact same device, the nozzle would be up here, the electrodes would be inserted right into this part, and the electromagnetic pumping was actually occurred by providing the current and the fields here in order to get this molten silver in the vessel to pump up through that nozzle. So you can see there's, even though this was back in April and May, it was very similar in concept to some of the components that we have today. So again, if you look for the gas supply, in the new model, the gas supply was achieved by putting it in the glove box with that atmospheric concentrations that we needed for it to happen. And if you took a look at the ignition system, again, you would see that if you look down into that vessel, just pre-ignition, you would see those two electrodes in there. So a lot of it looks like what you've seen earlier. But what's of interest here is that we wanted to make sure that the science that was being done as independent validators could in fact be reproduced by anybody. And in fact, if you were an objective scientist interested in finding out the truth in doing your validation and investigation, how would you approach it? And of course, what we found when we came is that the black light and brilliant light power scientists were already doing outstanding scientific method. So all we had to do was pretty much go in and take those measurements ourselves. So to determine, I guess the two main things to remember, if we wanted to try to simplify this whole thing down to a business or a lay audience, is that we want to look at what is the power output and what is the power input. Okay, so we looked at all the power inputs, being the heater, the electrodes, the pump, as they were all available in a digital oscilloscope information, so that we had tons and tons of data captured at very minute time frame. And then we wanted to look at how is the cooling system heat gain definitely an indicator of changes in power output of the system. Because if we have a steady state system where we're putting in a fixed amount of power, then we can take a look at those changes in that cooling system power, and basically that's a direct indicator of how much power is coming out. So let me talk about the independent validations. As I mentioned, Dr. Joseph Rennick is here today. Dr. Kandalam Ramanajishari is here as well today, and I'm here. Dr. Booker's not present, but you'll be able to talk to any of us. You can see the time frames in which we did our independent validations here at Brilliant Light. And with that, let me just go to, I'm going to do is just provide a quote from each of the independent validation reports that are available on the website, and then show a little bit of the graphics that each of the validators created that make them convinced that the power here is of a great amount of energy. And so one of the nice quotes from Dr. Rennick's presentation was how this nice aspect of this experiment, which I'll let you read it yourself, but you can see that he's basically identifying how simple it is from someone coming in from the outside to be able to see that there's something really going on here of a significant magnitude. And oh, by the way, not only is it easy to take these measurements of all the input power, but if we take a careful look at the changes in the cooling system, which is basically the output power that has to be taken away from the device so that it doesn't melt down, we'll be able to see a really good way to figure out the thermal output of the reactor. And if you take a look at this is basically the device being heated up by all of its auxiliaries, its inductively coupled heater, et cetera, et cetera. And then when we get to the point where there's ignition, it goes off the chart. And in this example here, you can see how it went off the chart. So the real challenge becomes to, well, what was the steady state power? And that will relate to our input power. And then what happens when we get these spikes? Because this drawing right here is basically a blow up of the spikes. And so if you take a look at these slopes, it's a very well understood and well documented way to create this relationship between input power and changes in input power as a direct proportion in relationship between the slopes in these lines. Dr. Chari did probably the most reaction observations of all of us. And basically, one of the also significant contributions being in our chemistry department at Rowan University, and the chair of the chemistry department, is that he makes this amazing, wonderful claim here that if we were to look at the reduction of the reactants that are actually involved, because a lot of people think, well, what about all this chemistry? You know, you're putting all this silver in, you're putting these proprietary, reactants and catalysts, and you're putting in hydrogen. Well, what would happen if we were to take a totally objective analysis as a scientist, if we were to get the most energetic reaction out of all of those components? And you can basically see from his report that would be a trivial power contribution, less than 20 watts. Okay, this is very significant because the numbers that we can see from Dr. Rennick's work is that we have an input power of about 7 or 8 kW, which you'll see very common in many of the validation studies, because if everything's on and everything's consuming power at the time, then you'll be in this anywhere from 5 up to 8 or 10 kilowatt range in terms of input power to the device. So when you see output power gains, as Dr. Rennick did, of 2 million watts or 645 kW, you see these 100 or 200 or 300 time gains in output power, you know that something very significant is going on. Obviously, nowhere near the reaction of available elements in that reaction chamber. So again, if we look at Dr. Shari's results from multiple validations, you can see that the input power ranges between 7 and 10 kW, and output power ranges between 126 up to 5 megawatts of power, depending upon which ones of these specific slopes we take a look at when we have these amazing power bursts from the device. My own contribution, again, you'll see a few of my runs that show many times power output than input, but also we note that we see more continuous operation in the cell. Sometimes these bursts were lasting minutes, 7 minutes. I mean, obviously you've seen video now where the newest device is able to run for hours. But at the time when we came as independent validators, we were actually able to see multiple minutes when this was happening. So again, some of the earlier experiments Blacklight did before they've sort of tweaked the specifications on how to maintain and maximize and optimize this reaction, they were getting bursts, in a very instantaneous burst, but that was a long time ago. Now they're at the point where they can make it happen for a long period of time. So in my experiments here, you're able to see that I too was able to get on the order of 65 to 150 time power gain, well over a megawatt in the larger scale for this reaction. Again, Dr. Booker, little note here is you could actually see this in the original sun cell. So he basically sees, going from this red-orange color, hearing a very loud explosive type, as it gets really exciting, and then a sort of a green color, and we got some pictures here that we took when we were validating. And silver vapor seems to come out, because again, remember, this is in the glove box. It didn't have the nice containment that the team has designed now, but it was basically in the glove box, and he saw an explosive stage lasting for about 30 minutes. And I actually got a chance to view that video, because that one was actually a video document. It took a long time to download that, by the way, when I was trying to take a look at it. But again, Dr. Booker, again, showing anything from 26 to 200 to 600 times the input power in these output power gains, extending for significant periods of time, and again on the order of hundreds of kW to megawatts here, 2 to 3 megawatts. So some of the other things that we observed, I mentioned here, these continuous operation, which has been independently validated now by us. Obviously, the Brilliant Light Power scientists have extended this almost indefinitely, depending upon how late Randy wants to stay here at night. But the other things that we observed quite significantly too was the welding of the electrodes. Again, had to have many thousands of degrees in order to have that happen. Obviously, seeing total destruction of the vessels, which brought a lot of our observations to a really quick halt. And so, again, I would like to see if there's any questions from the audience. I think I used my 15 minutes. Yes?
I see a lot of the experimental evidence. Did you do modeling that told you it should have been 3 megawatts or 5 megawatts that would have confirmed your measurements?
I did not do any modeling. Did either of the two validators? Dr. Rennie? What's that?
That was at the national lab. National lab thermal transfer, heat transfer.
Yes, some others may have.
So there was modeling done separately, and these experiments
Yeah, they
achieved the levels that the models predicted?
Yeah, I can answer. So we had the most noted expert I know in heat transfer, and sort of intuitively, the question is if you're looking at there's a inductively coupled heater antenna around the device, and then the question would be if the temperature rise rate with time doubled, does that mean you have twice as much power? And then he modeled it and showed that was the case for our particular design, looking at all the different heat transfer mechanisms that if you had 10,000 watts and you looked at the slope, and then you had 1,000,000 watts and you looked at the slope, was it scalable? Was it linear scalable? And do you have that multiple of 100 times more power by having 100 times more slope? And he proved mathematically it was.
I guess I was just going back to your astrophysics and,
Yes.
and the theory that expecting a certain amount of energy release from these transitions. Did you calculate that, and is the experiments matching that? That's, I guess, my
Yes, they are. And the other thing is we did it multiple methods. If you watch the June 28th, we did a live demonstration of that particular measurement where we measured the slope with all the parasitic loads, the electromagnetic pump, and the inductively coupled heater, and the ignition system. And then we compare that slope to the slope afterwards, and from that initial slope multiplied times that power and the ratio thereafter, we could get what the output power was. And he proved mathematically that they were linearly proportional. And it's not going to be a perfect model. A perfect model would be the next step we're going to, which would be a thermal power measurement on the black body radiation emission, which we're moving to. But we've done a lot of other tests. The calorimetric test shows the same magnitude of power. The optical, which we've now done with a NIST-calibrated halogen lamp and a deuterium lamp, I think is a fixed slit width, I think is infallible measurement on the optical power. And we're getting that, I think the calorimeter measurement, we're doing a decay on the current, because you do get a reflected power wave from the AC current that excites it. But now we're doing the input energy calculation using the current decay, which doesn't take into account any reflected wave. It's looking the direct amount of energy is actually flowing into the calorimeter. And I think that's pretty infallible. We added that as well, and Peter used that analysis. But all three methodologies give you the same order of magnitude of power.
Yeah, that's a good point. I only extracted from our reports the specific sun cell work. So I didn't include all the validation of all the other experiments, which went much further than that. And I think we have a question here, and then we'll go to you. Yes.
Yeah, I was just curious. I think all of this has been about power. Have you done any energy balance validations, like total energy in and then energy
Yes, we did
out?
energy in and out. Yes.
And what were those ratios?
It's huge numbers. Like even with the heater running for a very prolonged period of time, these experiments had a short duration. They were transient due to the fact that the vessel melted
Exactly.
and vaporized. But even then, we were getting multiples like 50 times more energy, total energy out than total energy in.
And with these new six
And I have a
runs,
report. I have a report I can share with you on independent analysis of
But
that.
that would
Yeah,
be
if you-
fascinating, because people pay for energy, right? They don't pay for power.
Right, I know,
Right,
but
right.
what it had that power ran for any amount of time, the only energy balance that would have gone into the equation was how much energy it took to melt the silver for startup compared to how much energy you got out. The amount for the silver melt up is very small. It's like 10 kilojoules or something like that. It's very, very small. In comparison, the amount of energy, once you have a megawatt, you're getting 1,000,000 joules per second. So it really dwarfs it very, very quickly.
Yeah, we did have calorimetry experiments that are in our validations. And again, if you wanted to take the area under the curve here, you could compare that back. You could compare that back, and that could be done, but we didn't.
Is there any problem in reproducing the calorimeter results? There used to be well, I'm just curious, is it easily repeatable, the experiment?
Yes, when we did all of the calorimetry for the silver shot blasts, we had many controls, which we compared all of the actual reactions to. So it was very easy to, replicate those the controls, and then also to see experiments, always in the order of magnitude significantly greater than what was input power. Thank you. Yeah, go ahead.
In the case that a reactor has been run for 30 minutes, what is the output power and where is that being sunk?
Into the cooling loop? Is that what you were asking about? Or?
We talked about a reactor having been run for 30 minutes. That's producing power, like megawatts of power, in which case, where are you sinking that power?
These didn't run that long. They vaporized.
No, I understand for the validation.
Yeah, so
but
for
it
the
talked about-
validations, we were basically looking at the water that was going through the cooling loop.
Sure.
And the cooling loop was discharging that into the loop.
Understood,
So
but there was reference to subsequent operations of the unit.
Oh, you're asking me?
For 30 minutes, sure. Yeah.
Well, with the new design, yeah. So which system are you referring to? The new dual injector
reactor,
system?
Any reactor that is run for 30 minutes,
Well,
producing megawatts of power. It's a lot of power to just dump somewhere.
Well, you can't make megawatts of power in this system without vaporizing. You have to go to the pure refractory materials, and then we had to go to the refractory material in terms of and molten electrodes in terms of the injection system. So none of them have run more than like on the order of a minute, and they vaporize. The cell vaporizes, and electrodes vaporize.
So the reference to 30 minutes is some other thing that's
We've run it much longer than that. That's the injection system and the ignition system are very, very low power where we don't put a lot of fuel into it. We just run at very, very low levels of power. And that was a request from industry partners to run something of a very long duration, just to prove that the engineering systems work. So there's
I understand
tested
that,
engineering
I understand.
systems, and then there's actually making power.
I understand. I guess the misapprehension I got was what I think other people may have also thought was that the reactor had been run for 30 minutes, producing power.
This reactor had been putting out for 30 minutes, whether it was putting out 3 megawatts was on.
Yeah, peak. There's like pulses of power, and then they would vaporize.
In other words, the reaction was sustained for 30 minutes, but not necessarily at those high
Not at
power.
that level.
Okay.
Not at that level. And then even you saw the one from July 20th demonstration at Columbia Technologies, that only lasts like 20 seconds, and vaporized the electrodes and vaporized the cell. And that was putting out that order of magnitude of power. But when you're putting that kind of power out, you're basically, it's like an explosion. It's like vaporizing everything. Yeah, it's like a disintegration ray at that point. So and you could hear the alarm going off in the glove box, and the glove box trying to maintain the balance against the huge pressure surge from the thermal heating inside that contained glove box. So yeah, the power balance works out by 3 different methods, and you kind of, when you're putting that kind of power out, you know it's a lot of power. The cell doesn't last very long.
If this experiment was run again today using this device, which appears to be much more stable and continuous, these experiments should be a lot easier to run and much more stable, if I'm guessing right. Is that right?
I would absolutely agree. Yeah, that we should be able to get much better information from this in terms of what its continuous power output is at some of those you know, actually the 16-minute video that we saw, we would be able to find many ways to characterize how much power and energy are coming out of that over the 3 to 30 minutes, you know, 6 hours or however long it was run. And I do believe that brilliant light scientists are, you know, trying to set up a way for validators to come back for their new device in the near future. So, thank you. Yeah.
When the reaction is occurring, what percentage of the energy is heat, what percentage of the reaction is visible light, and what percentage is black light?
Well,
Yeah,
I think based on a lot of the work that we did in the validation reports, as Dr. Mills pointed out earlier, the greatest majority of the energy is in the ultraviolet and extreme ultraviolet range based upon the spectroscopy that we did while we were here on the single shots. And it's not much of an assumption to make, but assuming that's the same reactions, which we believe it is, that's going on in the sun cell, we would expect that the biggest majority of it is going to be, you know, emitted in that range too. And then there's obviously a significant amount of heat that also comes out of that reaction. So because it's interacting with all of the other materials that are around at the vessel that it's, you know, that the reaction is taking place in. So, but the times of duration for our validations were short enough that, you know, we didn't get pushed out of the room by the heat or anything. So it's a lot of it's light, significant. But we didn't quantify all those percentages as independent validators. Good
Yeah, I
question.
can answer more those types of questions at the end. Because we did do some spectroscopy and characterization over time and things like that, so I can pick those up.
Well, thank you very much.